buffer solutions. Buffer solution is a solution which has the ability to maintain its pH when a small amount of strong acid or strong base is added to the solution. There are two types of buffer solution. First, acidic buffer solution. It contains a weak acid and its salt or its conjugate base. The second one is basic buffer solution. Basic buffer solution contains a weak base and its salt or its conjugate acid. Acidic buffer solution, as I've mentioned before, it's a solution that contains a mixing of weak acid and its salt or its conjugate base. For example, here we have CH3COOH. This is weak acid, and its salt CH3COO. Why or its conjugate base? Because if you look at here, this is acidic buffer solution. In here, you have the weak acid CH3COOH and you have the salt. We know that salt will be dissociated into cation and anion. So in this acidic buffer solution, you have Na+, the cation, and the anion CH3COO-. So this is its conjugate base. For weak acid, this is its conjugate base, and you have salt in it and you have water in this acidic buffer solution because they are in aqueous form, so you have water in this solution. And then here, this is the equation for the salt, dissociation of the salt, CH3COO-Na dissociate into anion CH3COO-, or you call this conjugate base, because this is conjugate base for this weak acid, plus the cation Na+. And then, now here, CH3COOH, the weak acid, dissociate in water to form H3O plus CH3COO-. So that's acidic buffer solution. How it works: when a small amount of strong acid is added, H3O plus is added in this solution, in acidic buffer solution. H3O plus dissociated from strong acid will neutralize CH3COO- ion or conjugate base. So this H3O plus comes from strong acid because you add a small amount of the strong acid. That H3O plus from strong acid will neutralize the CH3COO- ion. Because this is plus, so it will react with the CH3COO- ion. So here you have the equation: CH3COO- ion reacts with the H3O plus, negative ion react with positive ions, and you get CH3COOH. It will form the weak acid plus water. As this reaction happens, the concentration of CH3COO-, the concentration of this, the CH3COO- ion from this salt, CH3COO-Na salt, and from CH3COOH weak acid, you have two sources. One CH3COO-, one the source is from the salt. Second, CH3COO- source from the weak acid. So you have two sources to get CH3COO-. When you add strong acid, H3O plus from the strong acid will react with CH3COO-. So when it reacts, this CH3COO- concentration will decrease because it will be used up by H3O plus. So this concentration will decrease and the concentration of weak acid will increase because these two keep producing CH3COOH and water. So the concentration of CH3COOH will increase, the concentration of CH3COO- will decrease. And then when this concentration of acid increase, we expect that the pH will be lower. Because you have more acid, we expect that the pH will be lower. But this is how the buffer works. It won't affect the pH that much. How? This concentration of weak acid, it will keep dissociate in water. This weak acid keep dissociate in water to produce again CH3COO- and H3O+, and this will use to react with H3O+ again, and that's why the pH is not much affected. Because when the concentration of weak acid increase, you use this weak acid will dissociate in water and produce CH3COO- and H3O+ again. So that's why pH is not much affected. This is how the acidic buffer solution works. And then, that's when you add the strong acid. When you add strong base into this acidic buffer solution, when you add strong base means in there you have OH-. That OH- will be neutralized by the acid CH3COOH. So this acid CH3COOH will react with OH- to become CH3COO- plus H2O. So this OH- will accept one proton from CH3COOH to become H2O and CH3COO-. When this reaction happens, when the OH- react with this weak acid, the concentration of this weak acid will decrease, and the concentration of CH3COO- will increase. When this concentration decrease, so CH3COOH will dissociate into the water and to produce H3O+ and CH3COO-, we have this dissociation equation. This is reversible arrow. So when the concentration of CH3COOH decrease, this will be converted to become CH3COOH. The equilibrium position will shift to the left. This will convert itself, reacts with H3O+ and becomes CH3COOH again. So that's why the pH is not much affected, because when this increase, this equilibrium position shift to the left and make more CH3COOH again. So that's for how acidic buffer solution work when you add strong base. When you add strong acid, it will react with CH3COO-. When you add strong base, OH- will react with the acid to neutralize. Base react with weak acid to neutralize again, and this equilibrium position will shift to the left because this concentration decrease, so equilibrium shift to the left. So the pH is not much affected. Henderson-Hasselbalch equation for acidic buffer solution. We know that for any weak acid, for example HA, any acid, the dissociation equation Ka expression are product over reactant. For this equation, reactant HA weak acid dissociate in water, reversible arrow, because weak acid very slightly dissociate, so we use reversible arrow. The products are H3O+ and A-. This is the conjugate base. Weak acid donates proton, become A-, the conjugate base. And the products, both aqueous products over reactant, that is the Ka expression. So this is the Ka expression. In order to write down the Henderson-Hasselbalch equation, from this expression, you take H3O+ concentration to the left and you move this to Ka, it will become Ka times HA concentration over A- concentration. Weak acid over conjugate base concentration. That is the concentration of H3O+. You just rearrange this equation. H3O plus as the subject, rearrange the equation. And then we know that we put the log, negative log H3O plus, put all log here, negative log H3O plus, negative log Ka, plus negative log, because here times, so plus negative log HA over A minus. So you put negative log for all here, for all component here, you put negative log. And then we know that negative log H3O plus is pH. pH equal negative log H3O plus. And pKa is equal negative log Ka. pKa equal negative log Ka, pH equal negative log H3O plus. And then, so from here, pH equal pKa plus log, because you want to cancel out this plus and this is minus. So when you put pH, pKa plus log A minus concentration over HA concentration. So this is Henderson-Hasselbalch equation. This is for acidic buffer solution because you have pKa here and weak acid concentration, conjugate base concentration. This conjugate base concentration can also be the concentration of the salt. This concentration can also be the concentration of the salt, concentration of conjugate base, or concentration of the salt. This A minus on top here. Example, weak acid CH3COOH and CH3COO and A. This is the salt, this is the weak acid. Salt, one direction arrow, dissociate into CH3COO minus plus and A plus. Anion, cation, or aqueous form. Weak acid, very slightly dissociate in water, so reversible arrow to becomes H3O plus aqueous plus the conjugate base. This acid donates a proton and it becomes conjugate base COO minus. Now, start with the Ka expression, product over reactant, ignore H2O because H2O is in liquid form, so you don't have H2O here. Only take the aqueous. And then rearrange the equation. You'll get H3O plus equal Ka times CH3COOH over CH3COO minus. And then, as I've shown before, the Henderson-Hasselbalch equation is this. pH equal pKa plus log conjugate base over weak acid. Here. Conjugate base or salt over weak acid. So this is the equation. And just substitute our conjugate base or our salt is CH3COO minus. Why I say that salt or conjugate base? Because here conjugate base and you have this here from the salt. So that's why salt or conjugate base. So CH3COO minus over weak acid concentration CH3COOH. Example, calculate the pH of a buffer system containing 1 molar CH3COOH and 1 molar CH3COONA, given the concentration of weak acid and the concentration of the salt. The question asks us to calculate the pH of it and what is the pH after you add 0.1 mole gases HCl to 1 liter of the solution. So this one given is the number of mole and the volume, not the concentration. So you need to find out the concentration of HCl from information of number of mole and the volume. Assume that volume of the solution does not change when HCl is added. So the volume 1 liter, maintain. Ka value is given. So we know that initial concentration 1 molar for weak acid, initial concentration for the conjugate base CH3COO minus, from here conjugate base or the salt is the same, concentration is 1 molar as well. So we need to find out the pH, so we can use Henderson-Hasselbalch equation, pH equal pKa plus log salt over concentration of salt or concentration of conjugate base over concentration of weak acid. So we have the value of pKa. pKa is negative log of Ka. Okay, we know pKa is negative log Ka plus log the concentration given 1 over 1. So this pH is 4.74. That is the pH for buffer containing CH3COOH and CH3COONA. This is the pH. Next, we need to find out the pH when you add 0.1 mole of gaseous HCl. When you add this, you need to find out the concentration. So the concentration is 0.1 mole and then this liter. So 1 molar times 1 liter is, this is the mole of CH3COOH. Because we have 1 molar CH3COOH times 1 liter, because the question said the solution, volume of solution does not change. So we have to find out the number of mole, because we need to know how many mole of this react with the HCl. So that's why you need to find out the number of mole of CH3COOH first and number of mole of CH3COO minus. We have the concentration of both CH3COOH and the concentration of CH3COO minus, same as the concentration of the salt. So you times 1 liter to get the number of mole, and both are 1 mole for CH3COOH and CH3COO minus. Now, from here, we don't have, the concentration here is not given. We have the number of mole. We know that HCl is strong acid. Strong acid completely dissociate. So completely dissociate, one direction arrow only. So HCl, H2O becomes H3O plus plus Cl minus. So when this HCl is 0.1 mole, you balance this equation. When HCl is 0.1 mole, balance the equation 1 mole, 1 mole, 1 mole, 1 mole. So when HCl is 0.1 mole, H3O plus is 0.1 mole, Cl minus is 0.1 mole. So that H3O plus you add into the buffer containing CH3COOH and CH3COO minus. Add in there that H3O plus from HCl will react with CH3COO minus. Positively charged ion react with negatively charged ion in the buffer solution. So when it reacts, it will produce CH3COOH. This is conjugate base. So this is acid, conjugate base. So it will become neutralized, become CH3COOH plus H2O. And then, now, H3O plus react with CH3COO minus, CH3COOH plus H2O. From this equation, you need to find the pH. So you need to construct the ice table. We don't have the molarity, so we can put the number of mole. And you can put the molarity here, but here I put the example of the number of mole. So number of mole here is 0.1, because you get from here 0.1 mole, because given here 0.1 mole, so you get 0.1 mole H3O plus, and then initially 1 mole. Here 1 mole, you calculate from the concentration is 1 molar and the volume 1 liter, because volume of solution does not change when the HCl added, so this one maintain 1 liter. 1 mole CH3COO minus and 1 mole CH3COOH. Ignore water. And then change is in concentration. This you have 0.1 mole. Here you have 1 mole. If you look at the stoichiometry, 1 mole will react with 1 mole. So this 0.1 mole, if you only have 0.1 mole, will react with only 0.1 mole here. So that's why negative 0.1, because it will decrease. You only have this amount, so only 0.1 mole means you use up all H3O plus here, negative 0.1, and here 1 mole. So if you have 0.1, here 0.1 mole also will be used up. Not all 1 mole, only 0.1 mole will be used up. And then here, here stoichiometry 1 mole, 1 mole, 1 mole. If you use 0.1 mole, react with 0.1 mole, it will produce 0.1 mole of product. So that's why plus 0.1 here. And then final 0.1 minus 0.1, 0, 1 minus 0.1, 0.9, and here 1 plus 0.1 is 1.1 mole. Note that these are the number of mole. To calculate the pH, you use the Henderson-Hasselbalch equation, pH equal pKa plus log salt concentration over the concentration of the weak acid. So we have the Ka value 1.8 times 10 to the power of negative 5. pKa is negative log Ka plus log, here you have to put concentration. We have number of mole here, you don't have concentration. So to get concentration, number of mole divided by the volume. Volume is 1 liter, so 0.9 divided by 1, 1.1 divided by 1 liter. And you'll get the pH 4.66. Next, basic buffer solution is a solution that contains a mixing of weak base and its salt or its conjugate acid. For example, we have NH3 and NH4Cl. So in here, in basic buffer solution, you have NH3, you have NH4Cl. The NH4Cl is the salt. Dissociate, salt arrow, dissociate completely, NH4 plus Cl minus, 1 cation, 1 anion, or in aqueous form. So in here you have NH plus, you have Cl minus, and this weak base NH3 will be very slightly dissociate in water to become NH4 plus OH minus. So in this basic buffer solution, NH4 plus comes from the weak base, and this NH4 plus also comes from the salt. This NH4 plus, two sources, same like the acidic buffer solution. How it works: when a small amount of strong acid is added into this basic buffer solution, the H3O plus from the strong acid will be consumed by NH3, because our NH3 is base, H3O plus is acidic. So neutralization reaction happen. This NH3 reacts with H3O plus from strong acid to become NH4 plus OH minus. When this reaction happen, the concentration of NH3 will decrease. In this basic buffer solution, the concentration of NH3 is decreased because this NH3 is used to neutralize the H3O plus from the strong acid. When this concentration decrease and it keep producing NH4 plus, so the concentration of NH4 plus will increase. Means you increase the conjugate acid concentration. This is base, this is conjugate acid concentration will increase. So this is the equation, dissociation equation of NH3, because NH3 is weak base. So weak base dissociate very slightly in water to become NH4 plus OH minus. When this NH4 plus increase, this equilibrium position will shift to the left to make it normal again. So that's why pH is not much affected, because the increasing in NH4 concentration will be converted again into NH3 again to become normal again, because this NH3 decrease, so this is increased, equilibrium position shift to the left. pH not much affected. That's when strong acid is added. When strong base is added into the basic buffer solution, this OH minus from the strong base, OH minus from the strong base will react with NH4 plus. Our NH4 plus is conjugate acid. Base react with acid. NH4 plus react with OH minus to produce NH3 plus H2O. Now we know that when this NH plus keep reacting with OH minus to become NH3 and H2O, the concentration of NH3 will increase and the concentration of NH4 plus will decrease. So here, when this is increased, the dissociation equation for weak base NH3 very slightly dissociate in water to become NH4 plus OH minus. So this increase in NH3, this NH3 will dissociate in water to become NH4 plus OH minus. This will make the pH is not much affected because this is how it converts the NH3, the increasing of NH3 to become normal again by dissociation of weak base to become NH4 plus OH minus again. So this concentration will be back to normal again because initially it decreased here it's increased. It will become normal again when you use that concentration to dissociate into NH4 plus OH minus. Therefore, pH is not much affected. Hasselbalch equation for basic buffer solution. For any weak base, the dissociation equation and Kb expression are, so this is a Kb expression and this is a dissociation equation for weak base. Weak base dissociate very slightly in water, that's why we use a reversible arrow. To become conjugate base, it accepts 1 proton and OH minus. And the expression for Kb, products over reactant. You rearrange this equation to make OH minus concentration as the subject and equal to Kb times concentration of the weak base over the concentration of conjugate acid. And you put negative log for all, negative log OH minus equal negative log Kb plus negative log B over BH plus. So we know that POH is equal to negative log OH minus and PKB is equal to negative log Kb. And here you can rewrite POH equal PKB plus log because you want to cancel this plus negative plus log. This is a conjugate acid on top. Okay, you put this in opposite, so the bottom will become on top, the one on top will become at the bottom. So this conjugate acid concentration or the salt concentration over the weak base concentration. This is the Henderson-Hasselbalch equation for basic buffer solution. Example, NH3 and NH4Cl. NH3 is the weak base, NH4Cl is the salt. The salt NH4Cl will completely dissociate to become anion and cation. The anion Cl minus, the cation NH4 plus, all in aqueous form. Weak base dissociate very slightly in water to become conjugate acid NH4 plus OH minus. So here the Kb expression, products over reactant, and like I've shown here, you rearrange and I put negative log and you'll get POH equal PKB plus log salt or conjugate acid on top over NH3 concentration, the weak base at the bottom. This is Henderson-Hasselbalch equation for basic buffer solution. Example A, calculate the pH of the solution prepared by mixing 0.1 molar hydrozinium chloride, so this is the salt, with hydrazine. This is the weak base. So you know that salt and weak base, so this is buffer solution. You need to calculate the pH of the buffer solution. So this is basic buffer solution, so you need to use Henderson-Hasselbalch equation. Now, we have the volume and molarity. So, initial mole, you need to find out the number of mole of this first, because you don't know the molarity of the total. This is molarity for 500. This one is molarity for 500 ml. If it is buffer solution, you mix those two. If you mix those two, it's not 500 ml anymore. So you cannot take this 0.1 molar to substitute here. These two, you cannot substitute straight away here, because this equation is just for buffer. Henderson-Hasselbalch buffer solution. 0.1 in 500, 0.1 in 500, this is different. So when you mix, it's not 500 ml anymore. It becomes 1 liter. If you have the new volume, so you need to calculate the new concentration. That's why you need to find out the initial mole of this N2H5 plus N2H4. So here N2H5 plus, because you need the concentration of conjugate acid. Here is not written conjugate acid, you only have the salt and the weak base. So you have to write down the N2H5 plus, this one, you need to write down the conjugate acid form. Salt will dissociate to become N2H5 plus and Cl minus. So you need the concentration of N2H5 plus. Because the concentration of conjugate acid is equal to the concentration of the salt, because it completely dissociates. So that's why calculate the number of mole as 0.1 times 500 divided by 1000. Because you need in liter, so that's why divide by 1000. So this is the number of mole for 500 ml. This is number of mole for 500 ml. But if you want to put the concentration, this number of mole need to divide by the new volume. Our new volume is 500 plus 500, because you're mixing 500 ml and 500 ml. So that number of mole divide by the new volume 1 liter. So this is the concentration of conjugate acid, and the concentration of the base is 0.1 mole over 1 liter. This is the concentration of the base. And then you need to calculate POH. POH negative log Kb. Kb value is given 1.7 times 10 power of negative 6. So you will get POH. If we want the pH, 14 minus 5.47 equal 8.53. Next, calculate the new pH of buffer after addition of 2 ml of 0.2 molar NaOH. So we know that after that addition of 2 ml, this NaOH, addition of strong base. Our buffer is basic buffer, and you add strong base into that basic buffer. In there, you have NaOH molarity and NaOH volume. So for this one, 2 ml of 0.2, from there you can get the number of mole. Volume and molarity, you can get the number of mole because it dissociates completely, and water 1 mole, 1 mole, 1 mole. So you get from here, you get 4 times 10 power of negative 4 mole, and same 4 times 10 power of negative 4 mole, and 4 times 10 power of negative 4 mole. Our OH is 4 times 10 to negative 4 mole. This OH from the strong base is added into our basic buffer. In basic buffer, you have conjugate acid. Conjugate acid will react with that OH minus base. From the strong base, it will react, and it will form neutralization reaction. The products are N2H4 aqueous and water. Means this N2H4 concentration will increase, the concentration of N2H5 plus will decrease. We need to calculate the new pH. So here you have 4 times 10 power of negative 4 mole, 4 times 10 power of negative 4 mole, 4 times 10 power of negative 4 mole. Because it needs to be the same, because 1 mole, 1 mole, 1 mole. Okay, so the initial, that's the comparison. The initial, we have 4 times 10 power of negative 4. And for N2H5 plus, you have 0.05 mole. Okay, initial, you have 0.05 mole. Here, 0.05 mole. And then initial of N2H4, 0.1 mole. This one, initial 0.1 mole N2H4. And when you have this number, if you compare these three number of mole, the number of mole of OH minus is the smallest. So only this amount of OH minus will react with that amount with N2H5 plus and produce that amount of N2H4. Because the stoichiometry is 1 mole, 1 mole, 1 mole. So all of OH minus will be reacted with N2H5 plus. In N2H5 plus, you have 0.05 mole, but only 4 times 10 to the power of negative 4 will be used from this. Only this amount will be used to react with OH minus, because you only have 4 times 10 to the power of negative 4 mole. Only that amount will be used, and only that number of mole will be produced to N2H4. And then final, this 4 times 10 to the power of negative 4 minus 4 times 10 to the power of negative 4, final 0. And 0.05 minus 4 times 10 to the power of negative 4, you'll get 0.0496. And 0.1 mole minus 4 times 10 to the power of negative 4, you'll get 0.1004 mole. So here we need to calculate the pH. We know that POH equal pKb plus log N2H5 plus, the conjugate acid, over the weak base. So this is Kb, our Kb value, 1.7 times 10 power of negative 6 plus log, this is the new volume. Because the question doesn't state that it does not change. So initially we have 1 liter, 500 plus 500. And we add new and AOH. So it becomes 1.002 liter. So this is our final volume. So you have this number of mole of this conjugate acid, final 0.0496 over 1.002 liter. This is a volume. And you'll get the concentration, mole divided by volume is the concentration, because you need to substitute concentration in here. And then this is the number of mole of N2H4 here, N2H4 divided by the final volume, 500 plus 500 ml plus 2 ml. You'll get in liter 1.002 liter. And the POH is 5.46. The question asks for the pH. So pH is equal 14 minus 5.46, and you will get 8.54.